Good afternoon, everyone. Thank you to the organizers for this conference. I'm Johan Fourdrinoy, PhD student at the Institut P', University of Poitiers. Today, I'm going to present to you the work carried out jointly with the LMR on the deadwater effects and more precisely on the breaking of internal waves within this phenomena. So to begin with, I would like to come back to observations of boats pulled in a shallow and single layer water. A boat moving at constant speed generates several wave systems, a stern wake and also a bow wave. These waves will depend on the boat's speed and on characteristic speed of gravity waves. From these two speeds, we can define a Freund number. And as the Freund number increases, the amplitude of the bow waves increases too, up to critical speed where Freund equals 1. Passing this critical value, the boat starts to ride the bow wave. And during experiments in a towing tank, we observed the breaking of the bow wave when the amplitude became too strong. This increase in wave amplitude causes there's an increase in wave drag. In the figure on the left, we see a drag crisis which occurs for Freund equals 1. This is an analytical calculation according to the Sretensky H theory. And we can draw a parallel between this behavior in monolayer and the behavior on a boat in a bilayer. In the presence of a density stratification, we also observe a crisis of resistance for a Freund number close to 1, but this time the Freund number is defined by the characteristic speed of the internal wave, depending on the density gradient and on the depth of the two layers. This crisis of resistance is not due to the generation of a surface wave, but to the generation of an internal waves. We experimentally carry out a stratification in an aquarium, and in this video, we can see a boat model pulling in our aquarium. So we can distinguish several behaviors for low towing force. So video on the top, the boat generates a very low amplitude deformation of the interface. So just here. For the larger towing forces, so bottom video, I can just come back. So for larger towing forces, the boat initially generates a wake, but quickly overtakes it. Then we observe a weak depression under its keel. The boat rides the internal bow wave, like in monolayer when the boat rides the surface bow wave. Finally, more specific behaviors are observable for the medium towing forces. With these forces, the amplitude of the interface deformation is large, the boat is slowed down considerably, and we can even see pitching just here. If we measure the speed of the boat over time, we can define three behaviors. In the first, when Freund number is small in front of 1, called the subcritical ballistic regime, the boat reaches a low asymptotic speed. In the second, called the oscillating regime in yellow here, the speed of the boat oscillates around an average speed close to Freund number equals 1. And finally, in the last, called supercritical ballistic regime, the boat reaches an asymptotic speed where the Freund number is greater than 1. It's necessary to use a corrective term in front of the characteristic speed of the internal wave. There is a factor of 0.8 between theory and experience, a factor which is still unclear, but which is common to the other work in the scientific literature, and we are not dealing with this point today. We were interested in the interfaces deformation, so we use a subpixel interface position measurements method, which can measure deformations of the order of 10 micrometers. On this slide, you can see on the left the space-time diagram of the deformation in a subcritical case. In black is represented the position of the boat. We observe two wave systems. So the first is what we will call the Nansen wake. This is a classical internal wake glued to the boat and depending on its speed. And the second is what we will call the Ekman wave. It's this depression escaping of the bow of the boat and followed by a wave train, just here. Using a Fourier transform, we can move into the spectral domain. We find again our two systems. The Nansen wake provides energy around the advected branch, just here in purple. The adjective branch has a slope equal to the board speed. And the second system, the Ekman wave, provides energy around an S-shaped branch, which is characteristic of dispersive effects. This branch is predicted by the linear Stokes dispersion relation. And we have shown that the Nansen wake is only a stationary effect associated with the board speed, while the Ekman wave is only transient and due to the initial acceleration. Thus, from a linear model, it is possible to find the different deadwater behaviors, whether for simple ballistic regime with just an asymptotic speed or capricious regimes with speed oscillations. A linear description is sufficient to set up an analytical computation. And from this calculation, we have shown that the Ekman wave only plays a transient role in the behavior of the bots. And in this model, in this linear model, after a long time, the Ekman wave and the bot separate. We carried out numerical experiments for various parameters. The various laboratory experiments were carried out for Y canal with a beam width ratio equal to 0.27. It's this one. If we perform the same experiments, so the same stratification in a narrower canal, the amplitude of the Ekman wave increases and the amplitude of the nonsense waves increases too. We also notice that the dynamics of the boat are modified and the speed oscillations gain in amplitude and in frequency. Thus, observation of deadwater effects are accentuated by the use of narrow canals in laboratory, but outside laboratories, we find this problem in the entrance of harbor, for example. Increasing the wave amplitudes will introduce nonlinear effects that can go up to breaking waves. These internal breaking waves will modify the behavior of the boat and also introduce new hydraulic or wave structures. In this video, the experiment was carried out in a very narrow canal with a beam width ratio equal to 0.9. The amplitude of the Nansen wake becomes very, very important, and the boat is slowed down considerably, giving the impression of a sudden stop. The keel of the boat acts as a forcing boundary condition for the wake, which deforms to create a breaking wave, and the boat accelerates again and later reproduces the same behaviors, slowing down deformation of the wake, breaking internal wake. Sometime during a breaking internal wake, we can see Kelvin-Helmholtz instabilities. Oh, I have bug. Sorry. I can't use my computer.
Oh.
Do you hear me?
Yes, we can hear.
Yes, it's just, okay, so just WPS.
Okay.
Sorry.
Okay. Well, I think if you just want to reboot your computer, we can have a discussion in the meantime.
Okay.
Yes.
Okay.
It's frozen, right?
I just stop the chair, and when I can, I come back.
Yes.
Okay.
Yeah, no problem. Okay. So in the meantime, are there any comments on today's talks? Let's see. Marek, are you still there?
Yeah, I'm here. Yeah.
Actually, I had another question on your talk, if you don't mind.
Sure, of course.
So for the mode 2 waves, so you said you can control the height or the amplitude. So can you actually, in my mind, mode 2 waves are generally sort of small amplitude. Can you actually make, if you wanted to, large amplitude mode 2 waves?
Yeah, I mean,
Yeah.
in the examples that I showed, yeah, basically. Okay, so I mean, I guess it's a better way to answer that would be with a recipe, right? So if you want to make large amplitude mode 2 waves, have multiple picnoclines, right? So 2 in my case. So if you're smarter than me, you could use many more. Space them apart just the right amount. So David had a whole paper about sort of if you have a single picnocline, you almost invariably get breaking and a lot of dissipation. So if you move the 2 picnoclines apart, you can either enhance transport or decrease the actual large scale overturning. And then it's just the matter of having a fairly large region trapped behind your barrier when you do your lock release. So, you know, that's not to say, I'm not saying there are many large amplitude mode 2 waves in the ocean. I'm just using these as a convenient tool for the experimentalist. That's all.
Right.
Right. So the key ratios there, and I'm sorry, I didn't think of this when Adele asked earlier about it. It's the ratio between the propagation speed of the instabilities and the propagation speed of the wave. So, right. So for mode 1 waves, they're faster. And so everything is left behind. It's a convective instability, right? It turns out there aren't global instabilities here. They're all local instabilities or convective. So they drain out the back, but they drain out the back more slowly. So you have more time. It's more forgiving in terms of identifying, you know, the right times to look at it. Does that answer your question? Yeah.
Yeah, sure. I mean, it's very interesting. I'm a big fan of mode 2 waves, actually.
Yeah, they're really easy to generate in the lab, right? Every time I teach, I always use them. Yeah.
Yeah.
So
I mean, they're very stable also.
Yes.
I mean, at least, you know.
Yeah. No, it's good.
I mean, just another question. So what if you, let's say, go mode 3, mode 4? I mean, has that been?
I've thought about that. I've looked a little bit. So Kevin Lamb's in my department. He does a lot of work on shoaling. And so I've sort of asked him, you know, for examples where you see the even higher still. And we've looked a little bit. We haven't really found very energetic examples. So, you know, when I was in graduate school, it was all mode 1, except for a couple of old papers, right? There was a mode 2 paper by David Farmer, for example. So,
Yeah.
you know, now maybe we'll go towards higher mode still, but as far as the ocean's concerned, mode 1 wins and mode 2 is kind of a second favorite.
Right. Yeah.
Johan's back. So
yes.
Yeah.
So
Yeah, I come back.
Okay. So just
sorry.
Yeah, no problem.
So the same measurements are carried out as before. So time interface detection and measurement of the boat speed. And we still distinguish 2 wave system. Here it's the Ekman wave escaping from the bow. Here the Nansen wake, but with an internal breaking wave. As predicted by the simulation, the speed oscillations have high amplitudes, and wave amplitudes are also much greater in the presence of lateral confinement. However, the Ekman wave does not appear to be alterated by the breaking Nansen wake. The Ekman wave is smaller than the Nansen wake, so in order to be able to study it more precisely, we seek to generate it differently. For this, we were inspired by the work carried out by Scott Russell during his studies on a single layer boat waves. An object is placed at the extremity of the canal at the level of the interface, and by lifting it, we create a vacuum serving as an initial perturbation. This perturbation creates the Ekman wave, not being polluted by the Nansen wake, so we can measure the undulating dispersive depression over a long acquisition time. This allows greater spectral resolution. In the figure on the right, so we see the power spectral density of the interface detection, and we can see the S shape here. It's the S-shaped branch described above. However, it no longer perfectly follows the dispersion relation proposed by Stokes in blue. A correction introduced by Gru allows better fit to the observation. This correction takes into account a modified density gradient. We must take this correction into account because this presented experiment was carried out after the diffusion of salts from one layer to the other layer. In the previous experiments, the salt has not yet diffused. Indeed, the Stokes dispersion relation assumes a perfect belayer, so a clear density jump, and no mixed zone. Grew introduced a correction to take into account a mixing zone with a sloping gradient. It's what you can see just here. Typically, this mixing zone can appear following a breaking wave, or if salt diffusing between layers, so if we wait too long. However, the characteristic speed of the internal wave is not modified by the new gradient density, so the Freud number is not modified. The presence of a density gradient reveals new undulating structures. From the Buon-Vassala frequency defined by this new gradient, we can define new modes of the undulating depression called Baroclinic modes. In addition to their longitudinal components, these modes have a vertical component, and we can predict their theoretical dispersion relation. The zero mode correspond to the Ekman wave described above, and all these baroclinic modes are linear wave response of the initial perturbation. To generate these modes, it is therefore necessary to have a density gradient, but also to initially induce vertical displacements. In the case of our experience, these vertical displacements are produced by the sudden movements of the obstacle at the extremity of the canal. And the zero mode, so the Ekman wave, moves faster than the secondary baroclinic modes. So we will find the Ekman wave from frontal head, followed by the mode overlay, just here. Experimentally, we find in the spectral domain the theoretical branches of baroclinic modes. So the zero mode, the Ekman wave, the first mode, the second modes, baroclinic. From this internal breaking wave, a new structure will appear. So it's so it's a linear structure, but it's always a wave structure. And the question is, if we do a bigger impulsion, if the initial perturbation is stronger, do we see the following baroclinic modes or another structure? So we did it. By increasing the amplitude of the initial perturbation, the amplitude of the Ekman wave becomes such that it surges. From this internal breaking wave, a new structure will appear, no longer a wave structure, but an hydraulic structure. This is a bolus. It's a mass of recirculating fluid which moves along the interface. I think this bolus is similar to the internal wave mode 2 presented by Stasna in the previous talk. And the bolus is located in the mixing zone between saltwater and fresh water. And this mixed zone serves as a wave guide, and it's possible to follow the structure over a long time and even after a reflection on the wall. From the measurements, we can estimate the speed of propagation of the bolus. The speed is constant, but seems to present discontinuities during reflection on the wall. And we note that the speed of the bolus is greater than the speed of the secondary baroclinic modes. In the spectral domains, just here, we can also easily distinguish bolus from a baroclinic mode because the bolus provides energy around an advective branch whose slope is equal to the bolus speed, and there is no the characteristic S-shape indicating the presence of a dispersive effects. From the spectral domain, we can try to isolate the bolus. For that, we carry out a filter around the advective branches, then use an inverse Fourier transform. This operation is not perfect because it is a gross method, but nevertheless, it's possible to estimate the size variation of the bolus over time. This size decreases until the bolus disappears completely. The bolus is therefore another structure that can appear when there is a density gradient and a vertical displacement. It is an hydraulic and not a wave structure. It's this time it's a nonlinear response to the breaking Ekman wave. So to conclude this presentation, in the phenomenon of dead waters, we can distinguish two wave systems. The first is an undulating linear depression generated by an initial perturbation. Here, the initial perturbation is the acceleration of the boat of the movement of the obstacle at the extremity of the canal. This linear wave will slow down the boat periodically, but it's only a transient effect. If its amplitude increases, it can be led to a breaking wave. This breaking internal wave leads to a mixed zone and the creation of a nonlinear heterogeneous structure called bolus. And the second undulating system of dead water is the internal wake. Like the surface wake, the internal wake causes a permanent drag, and by increasing in amplitude, it can interact with the boat and surge. This breaking wave could be the source of a second type of boat speed oscillation, but due to a non-linear structure. The question now is, are there any interactions between these nonlinear structures? Can the maximum of Ekman waves cause a break of the Nansen wake? This breaking wake, can it cause a pitching motion and therefore slow down the boats? We are reaching the limits of our linear model, and we need to do a new model with non-linearity to know the behavior of boats in dead water if we have lateral confinements, or to carry our experiments in a longer canal to dissociate Ekman wave and Nansen wake. Thank you for your attention, and sorry for the problem. And if we have time, I can answer questions. Thank you.
Thank you very much. Very nice talk. It's very yes. I think there's a question, Adele.
No, I'm sorry, it's still a clap.
Clap. Okay, very good. Thank you, Marek.
Hi, Johan. Very nice talk. I was just wondering, so you said at the end you thought that the boluses were hydraulic structures. I guess you showed a picture from Magda Carr's experiments. I guess we always interpreted it as the limit of of a breaking wave, right?
Yeah.
So it's true that it's kind of halfway between a wave and a gravity current. So my question would be, did you ever try doing multiple picnic lines, right? So you smeared your picnic line to get something like what Magda has, and I agree with you that it's a bolus. What if you did 2 picnic lines? What would you get?
With just two picnic lines, we don't try it. We have a perfect stratification or a multi-level stratification. And so I think if we want to do the same thing like you in your experiment, I think we need to try to do 3 layers.
Yeah.
With just 3 layers, but we don't try it.
Yeah, I mean, sure. There's lots of good reasons not to bother doing it. I was just on the offhand you tried it. I was just wondering. Anyway, thanks again.
Yeah, with a slope, with a density gradient, with a slope, we suppose it's like if we have n layers, so we can produce n-1 Baroclinic modes. And I don't know for Bolus if we have a difference if we have n layers or just 3 layers.
Right. The other question I had, and I know you probably said this somewhere, for what was the ratio of the boat length to the width of your channel for the confinement stuff?
The comparison between the size of the bolus and the size of?
No. The different question. You were talking about confinement, right? So it's kind of wedges.
Yes. Right? Yes, the confinement for first experiments we did a confinement of 0.27, and for the bolus it's always 0.27, but the obstacle, it's the canal is the same, but the obstacle it's all the canal, so it's a ratio of 1.
Right. Okay.
Yeah.
Thank you.
To have 2D structures and not 3D structures, because when it's here in our simulation, we have 3D structures and not for a ratio of 1. So it's easier to study this kind of experiment.
There was a question here in the chat, and they're asking, what is the density ratio between the 2 layers?
The fresh water, it's clear water, so it's 1 kilometers per liters, and for the salt water it's 1.020. 0.20. 1.020. Yeah. I think here you can have here
Yeah, right.
experiment.
In slide 13, if you go, can you please go to slide 13?
13. 13?
1-3, yes.
1, 3.
No, yes, I want to ask you on the wave number spectrum. No, I see straight lines, straight signature going through the.
Here?
Are those physical or it is leakage of the?
This one?
Yes.
Oh, yeah, this one. This one is Baroclinic modes. It's this one is the same of this one. Here we I changed the color map to see the Baroclinic modes, but here is the same. Is the same.
It's the same.
So this one you can see the S shape of the mode 1, mode 0, and mode 2. And here you have the influence of the surface waves. So it's dispersion relation of gravity waves, of surface gravity waves. You can have the influence just here because the movements, the initial perturbation, it's too strong, and we have a surface wave. Not with the bot, because with the bot, our bot, it's the speed velocity, it's lower than 23 centimeters by second, so we don't have a surface wave. But in experiments of Scott Russell, so this kind of experiments, the initial perturbation is too strong, and we have a surface wave.
Okay, thank you.